Before we do the next example, let us review some basic math first. This review will lead us to solve the next example. Let's go back to some of the exponential properties first. We know that e to the 0 equals 1. We also know that e to the infinity equals infinity, because e to a very large number is even a larger number. Also, we know that e to the minus infinity, that is equal to 1 over e to the infinity, because a negative exponent means 1 over that exponential function. But e to the infinity is infinity, so that equals to 1 over infinity, and 1 over infinity is 0. Now we would like to make it more interesting. So let's say that we have e to the j 2.5. This number is a complex number. Its magnitude is 1 and its phase is 2.5 radian. How about e to the j infinity? This is another interesting number. It is a complex number. Its magnitude is 1 and its phase is infinity. Now let us look at another complex number. Let's say that we have e to the 5 plus j 2.5. Now we can break the exponents into two terms, so this will be e to the 5 times e to the j 2.5. Now this is a complex number. Its magnitude is e to the 5 and its phase is 2.5 radian. The next two interesting cases will be used in defining Laplace transform. Let's look at the next case. Let's say that the complex number we have is e to the infinity plus j infinity. This is a complex number, so we can express it as e to the infinity times e to the j infinity. Basically, you break the exponent parts into two terms. Now this complex number, its magnitude is e to the infinity, which is infinity, and its phase is infinity. So basically, this number is infinity. The other case that we are interested in is e to the minus infinity plus j infinity. So when you break this number, you get e to the minus infinity times e to the j infinity. So again, this is a complex number. Its magnitude is e to the minus infinity, which is 0, and its phase is infinity. Because the magnitude is 0, then 0 times any value will be 0, so this number is 0. When the real exponent part is minus infinity, the magnitude is 0, and when the real exponent part is plus infinity, the magnitude is infinity. These two cases will be used to solve for Laplace transforms. Let us state the following note. The integral of the Laplace transform may not converge to a finite value for all possible values of s. It may converge to a finite value for partial region of all possible values of s. So now we are interested in a new definition called the region of convergence, which is abbreviated as ROC. It is the region of all possible values of s on the complex plane where the integral of the Laplace transform will converge to a finite value. So let us do example. Let f of t equals u of t, that's the unit step function. Find its Laplace transform f of s. We would like to find f of s using the definition, so we can say that f of s, which equals to the Laplace of f of t, that will equal to the integral from 0 minus to infinity of u of t times e to the minus st dt. But we know that u of t is 1 for all values of t greater than or equal to 0, then this integration can be expressed as the integral from 0 to infinity. We have replaced the lower limit from 0 minus to 0 because u of t is non-zero for t greater than 0. So we converted the 0 minus to a 0. And the u of t becomes 1 times e to the minus st dt. Now when we evaluate the antiderivative of this integral, it will equal to minus e to the minus st over s, and the limits of the integration will be from 0 to infinity. Now when we substitute for t, this integration will equal to minus 1 over s times e to the minus s times infinity minus the minus 1 over s times e to the minus s of 0. Now we know that e to the minus s of 0, which is the second term, will equal 1. But e to the minus s at infinity, which is the first term, is an interesting case. Remember that s, which is the complex frequency, is a complex value that is equal to sigma plus j omega. So to evaluate e to the minus s at infinity, which is the first term, we must substitute for s equals sigma plus j omega first. So this will give us e to the minus s at infinity, which equals to e to the minus sigma plus j omega times infinity. I replace s equals to sigma plus j omega. And now I can break it into two terms, so this will equal to e to the minus sigma at infinity times e to the j omega at infinity. The first term, which is e to the sigma at infinity, is the magnitude of this complex number. If sigma is negative, then minus a negative becomes positive, then that will be e to the plus infinity, and e to the plus infinity is infinity. But if sigma is positive, that means I have e to the minus infinity, because the negative of a positive is negative. So I have e to the minus infinity, which converge to 0. So to evaluate the integral of the first term, it will converge to 0 as long as the real part of s is greater than 0. So now the integral will equal to the first term will converge to 0, and for the second term we have plus 1 over s, and e to the 0 is 1, so we drop it, and this will equal to 1 over s. We have to stress that the real part of s, which is sigma, is greater than 0. So we have evaluated the transform of the unit step function u of t, and u of t is transformed into 1 over s. Again, we must memorize this transformation. A unit step function is transformed to 1 over s is something that should be memorized.